Chicago in the Flash Center. Sean is a Hubble Fellow at the University of Chicago for the last 3 years. I guess.
3? Well, 2, 3, something like that. 2, yeah.
Did his PhD at the University of Texas with Craig Wheeler. And today he's going to talk about quark collapse supernova. Sean is basically single-handedly implemented quark collapse supernova in Flash in a very short amount of time. So.
It doesn't feel short.
But looking forward to a good talk.
All right. Thanks, Evan. And Evan sells himself short. He's helped a lot, especially lately, with the stuff that we've been doing in Flash with quark collapse supernovae. And that's part of the reason why I'm here this week, is to work with him and push a paper across the finish line, which is very close. And thanks for the invite. I've enjoyed being here this week. I've enjoyed talking with many of you. And I've got one more day to go, so I'm looking forward to getting a lot more done tomorrow as well. Like Evan said, I'm going to talk about quark collapse supernovae, in particular three-dimensional quark collapse supernovae, what we're learning from 3D simulation, and where the field kind of is sitting right now. It's a very exciting time, simulation-wise, for quark collapse supernovae. And supernovae are really important for lots of areas of astrophysics. We think they're the fate of most stars above about 8 solar masses, give or take. They're birthplaces of neutron stars, magnetars, stellar mass black holes. Lots of interesting compact objects come out of quark collapse supernovae. We know observationally they're connected with long GRBs, and if you went to Chris's Chalk Talk this morning, he talked a lot about the long GRB mechanism and how that might originate in some massive stars. They produce heavier elements, and they might be the site of the R process. That's very debatable. They definitely make dust. We don't know how much. It's something to look into. They're going to be the fate of many of the first stars, which were overly massive. And so they might be some of the most distant objects observed with JWST, maybe. And they produce copious amounts of neutrinos, and also gravitational waves. So as multi-messenger observatories come online in the next few years, or, well, some like neutrinos are already online, but we might observe a galactic supernova in neutrinos or gravitational waves, which would be very exciting. The thing is, our theory of quark collapse supernovae is incomplete. We don't understand completely the mechanism that turns the collapse of a massive core around and drives an explosion. The leading candidate for this is the neutrino-driven mechanism, which I'll talk about a little bit. But so far, it's not universally successful, and it's not successful especially in reproducing the observational features of all quark collapse supernovae. So what are some observational features of quark collapse supernovae? We know a few things about them. They explode about 5 per second everywhere in the universe, integrated over the entire universe. We observe about 1 per day. And there's 4 times as many quark collapse supernovae as type 1a. They have large kinetic energies, typically 10 to the 51 ergs, sometimes called a beta, in honor of Hans Bethe, or a foe for 51 ergs. We know they have massive star progenitors because we've directly observed massive stars disappear after a supernova. So we know they have massive star progenitors. Their remnants, the neutron stars and black holes they leave behind, have kicks upwards of 1,000 kilometers a second. So they go zooming across the galaxy at high rates of speed. We know they radiate neutrinos, which means they create neutron stars. We know this because we observed the neutrinos from supernova 1987A, all 24 of them or so. Another important feature of quark collapse supernovae observationally is that they are all polarized. And polarization is sort of a measurement of the asphericity of the photosphere, of the emitting surface at which we're looking at. And the polarization is wavelength dependent, meaning spectropolarimetry. And so higher asymmetries are observed in the cores of these explosions. And this is just a little movie showing the P Cygni H alpha line. This is really blurry, and I'm sorry for that. I didn't make this movie. This is from Justin Mon. But I'm going to run this, and what you're going to see is this little caterpillar of red dots move across the spectrum and at the same time move through the QU plane, the Stokes parameters. And basically, this cluster right here is the interstellar polarization. So points around here indicate low polarization. Points away from here, way out here, indicate high polarization. And what this movie demonstrates is how this is actually wavelength dependent as this little caterpillar moves across the spectrum. You're going to see a larger polarization in the peak and trough of the P Cygni line. So as it zooms down here, it swings out in the QU plane and comes back around. And then on the peak side, it swings to the other side of the QU plane. And what you often see in the QU parameters for quark collapse supernovae is this dominant axis in the QU plane. So it's polarized but it's not sort of randomly polarized all over the QU plane. They tend to have a dominant axis. This is often interpreted as some sort of dominant axis in the actual geometry of the explosion, so a prolate geometry. And these loops, the fact that they're not going straight out and straight back, mean that there's actually some non-axisymmetric structure around that dominant axis in the explosion, which is also important. So not only is the polarization spectrally dependent, it's also time dependent. So this is just the integrated polarization, the net polarization of a type 2P supernova observed by Doug Leonard. And what we see is during the plateau phase, early on in the light curve, the polarization is consistent with 0. Early on in a type 2P supernova, we're looking at the photosphere in the hydrogen envelope, basically. We're looking at hydrogen. Once it recedes and falls off the plateau, the photosphere is receding down into the core, below the hydrogen. When that happened for this supernova, the polarization jumped up really high, almost discontinuously, and then it decayed. And this decay is consistent with just the photosphere disappearing and the optical depths dropping. So this decay basically indicates that the asymmetry stayed the same while the photosphere was disappearing. So the core of this explosion, according to the polarization, was much more asymmetric than the envelope, which was roughly spherical. Supernova 1987A, I already mentioned, it radiated neutrinos that we detected. But it was also polarized. And as we've continued to watch 87A over the last 20 years or so, we've seen the birth and the evolution of this young supernova remnant, sort of a proto-remnant. And we see that it is not spherical. There is definitely this elongation. You talk to the observers, there's a lot of stuff going on here that is hard to interpret. Effects related to dust. It's not clear if there's a lot of obscuration going on. But it's certainly not spherical. And of course, we all know the well-known ring around 87A, which lit up as ejecta slammed into it. That was a pre-existing ring. It's very possible that the progenitor was in a binary. And the progenitor was a very weird star. At least we thought it was very weird to be a core collapse supernova progenitor, a blue supergiant. That disappeared. So another nearby supernova, which we couldn't observe with modern telescopes, of course, and wasn't really necessarily observed in the historical record, but there's a lot of debate about this. But Cas A, it's a very young supernova remnant, maybe 300 years old, and we have some wonderful observations of Cas A, and it's a well-studied object and a wealth of information about core collapse supernovae evolution. So this is a composite image from Hubble, Chandra, and Spitzer, showing a multi-wavelength view of Cassiopeia A. But if you dig into this and you look specifically at iron K lines from Chandra, you see that there's definitely some asymmetric behavior going on here. There's these sort of clumps of iron, which are apparently diametrically opposed in the remnant. And here you can see them sort of in the cyan kind of greenish color. Tracy Delaney did this amazing rendering based on radial velocity measurements of several elemental clumps throughout Cassiopeia A, and made a three-dimensional map where here green is iron and the yellow is silicon, and then the red is just sort of the warm dust that's the rest of the remnant. And marked as the sphere is the compact remnant, probably a neutron star, but a black hole wasn't ruled out. So what we see is definite asymmetry, and there's these what have been called jets, which is sort of unfortunate nomenclature for these objects, but that's what they're called, are these jets of silicon. And what we see is clear evidence for overturn. There are heavy elements, silicon, iron, at higher radial velocities than lighter elements, carbon, oxygen, etc. So there is definitely overturn in the evolution of this progenitor. And something had to make this asymmetric structure. So all of this is merely to make the point that real core collapse supernovae are three-dimensional. They're not 1D, they're not 2D. There are three-dimensional structures in real core collapse supernovae. We know this from the time-dependent polarization, the loops in the QU plane, the elongated ejecta that we see in nearby supernovae such as 87A and Cas A, and a wealth of other observational evidence indicates that real supernovae are three-dimensional. So we have to understand this problem from a theoretical point of view in 3D. So what do we know? A little primer on core collapse supernova theory. Most of the core's original binding energy is a couple times 10 to the 53 erg. is going to come out as neutrinos in the first tens of seconds after the collapse of these cores. Now, the typical energies, I think I already mentioned, of core collapse supernovae, 10 to the 51. So you only got to trap about 1%, give or take, of this energy to explain typical supernova energies. But the problem is that that's a really tough thing to do. Neutrinos don't like to interact with normal matter, it turns out. So this is a really hard neutrino radiation hydrodynamics problem. It's coupled in nonlinear, and it's a really challenging calculation. We do have a few examples in 2D. So I should say that, before moving on, in 1D, the most sophisticated one-dimensional simulations of this neutrino radiation hydrodynamic problem don't find explosions, all except for the most itty-bitty masses. An 8 solar mass core, actually, you can get to explode in 1D. But I don't know how much I believe that progenitor structure. So this just doesn't work in 1D. It's too tough. The competing forces that are holding against the neutrinos won't allow you to get an explosion in 1D. But in 2D, things get better. So there's a handful of ab initio explosions in 2D, meaning that these are realistic neutrino transport calculations coupled to hydrodynamics, energy-dependent transport with realistic physics and interactions for the neutrinos. So it looked like things are a little bit better in 2D than in 1D. Now, the thing about these explosions is they're typically weak, meaning that they're well below 10 to the 51 ergs of kinetic energy. And they're characteristically prolate. They're extended often along the symmetry axis in 2D. There is a symmetry axis there. So some multi-D effects help. Lepton-driven protoneutron star convection down in the protoneutron star helps by enhancing neutrino luminosities. You're transporting more of that neutrino energy out quicker from the neutron star. Entropy-driven convection in the gain layer, where neutrino energy is actually being absorbed. So this is right behind the shock. That sets up a negative entropy gradient, which drives convection. And that can increase matter dwell times in that gain region. And integrated over time, you absorb a little bit more of the neutrino energy that's radiating from the core. And then there's a fundamental hydrodynamic instability of a standing accretion shock called the standing accretion shock instability, which can also aid explosion. And you don't need neutrinos. This is something that can be demonstrated with water in an experiment, and has been by Thierry Filglizzo. So this is just a hydrodynamic instability which causes the shock to wobble. And it prefers an L equals 1 mode, meaning that that's the fastest growing mode of this instability. And so it will wobble up and down that axis. And this can secularly increase the amount of mass in the gain region as it grows to nonlinear amplitudes. And that helps. That helps in getting an explosion.
Well, the non-linear development, I would agree, it's hard to disentangle
Yes.
from inverse cascade.
Absolutely. And I will talk about exactly that point later on in my talk. Although I think Rodrigo has done a very good job with this recent paper of doing that as best as can be done. All right. So 2D was better than 1D. Now we're entering the era where we can actually do 3D core collapse supernova simulations. I think this is a grand challenge for our current petascale computational astrophysics. But we still have to make approximations because they're still extremely expensive calculations. And these approximations come in various types, either approximations to the neutrino transport, which is the most expensive part of the calculation, and also the most common approximation that we make, or approximations to things like the hydrodynamics by decreasing resolution to make these simulations affordable. But what I'm going to talk about today, I hope will convince you that 3D makes an enormous impact on the dynamics of core collapse supernova simulations. But our current best evidence indicates that 3D is not the silver bullet, meaning that going to 3D doesn't solve all of our problems with the mechanism. We still don't necessarily find robust explosions. I'll talk about that more. So petascale computing, what do I mean by that? We're talking about 100 million zones or more in 3D. Which isn't that much, really. The biggest simulations go well beyond that. But here we also have to take of order 500,000 to 1 million time steps because the Courant condition is so limiting. So these really are a lot of computational cost to go into these supercomputing calculations. And I just want to highlight the folks that have been very kind to me in simulating core collapse supernovae. The folks at Argonne National Laboratory and the Argonne Leadership Computing Facility have supported my project by awarding me discretionary allocations to pursue these simulations. I just want to acknowledge them. And my main tool for the simulations that I'll talk about today is Flash, which many of you may have heard of. It's an open source code developed at the University of Chicago. It's been around since like 1997. It's got a long history in the astrophysics community. It's gone through several major revisions. It's currently version 4. And I just put up here a few things that we've done with Flash version 4 to make it capable of doing core collapse supernovae. Some important things are including the correct equation of state, which I got from Evan, including local heating and cooling to mock up the neutrinos in a light bulb fashion, which I'll talk about. Recently, Evan and I have implemented Evan's leakage scheme in Flash in multi-dimensions, and a source term to mock up the change in the electron fraction as these cores collapse. So lots of effort has gone into adapting Flash to be capable of handling this challenging problem. And an important thing is that it's open source and publicly available, and all the code that I have developed for doing core collapse supernovae eventually finds its way into the public release version. And there should be a release this month at some point, and it'll have, I plan, if I get the time to do it, all the code that I use to do the simulations I'll talk about today will be in that public release version, so you can go and try it yourself, see if I'm telling the truth. Okay, so what are some big questions that we want to address with three-dimensional simulations? Well, you know, the most obvious one is 3D more conducive to getting an explosion than 2D? Is that the answer? Do we have to do this in 3D? Is there something that we're not thinking about in 3D that's going to aid the explosion like we discovered in 2D? And generally, how different is 2D from 3D? Also, what is the dominant instability in core collapse supernovae? I've already mentioned the standing accretion shock instability, but there's also neutrino-driven convection, which is an exceedingly important instability in this context. And as Chris mentioned, it actually gets very hard to disentangle these two when they become nonlinear. So a lot of effort has gone into thinking and arguing about which is the dominant instability. In particular, which is the dominant instability in helping explosion, which is somewhat of a different question, I think. So I talked first about some 3D parametric simulations, which were some of the earliest approximate 3D calculations done first by the Princeton group, and then the Garching group attempted to replicate this calculation. And what the Princeton group found is that 3D was easier to blow up than 2D. Now, they used a very approximate approach for neutrinos. This is just local heating and cooling based on these source terms. And the leptonization was accounted for just on a density-based prescription, which actually works pretty well, but it's only meant for collapse. And these use realistic equations of state in 3D. So the summary of their results is that Princeton finds the solid curves on the left are 3D and the dash curves are 2D. So Princeton is finding that in 3D, it's better. The explosion sets in quicker and more vigorously than in 2D. The Garching group, on the other hand, didn't find such a clear result. Some of their simulations, 2D explodes faster than 3D. Some of their simulations, 3D explodes faster than 2D. And what they actually found in their results was that it was highly dependent on resolution. They found a really strong dependence on resolution. And they happened to use significantly lower resolution than the Princeton group. So a summary of these calculations and their differences. This is a lot of sort of wonkish stuff, which won't be that interesting to most of you. But there are some important differences. The fundamental hydrodynamics is different. They use a different grid structure. Gravity's the same. This is an important difference. The Princeton group used this YE of density prescription, both pre-bounce and post-bounce. The thing is, it's only meant to be used in the collapse phase, in the pre-bounce phase. That's where it's tuned. So the German group took that as an affront, and so they didn't change YE after bounce. And that changes the electron pressure quite significantly. So that's an important difference. And they talk about this, and they had to tune their results in order to get something that looked more like the Princeton group. Differences, and this is also important, I think, but resolution is also a big deal. So we had these two results on a very important question, and they disagreed. And I thought a while back that this might be a nice place to start with Flash and address this question and try to do three-dimensional simulations as close as I could to the Princeton group to try to repeat their result and see if 3D is more helpful. So of course I'm using a different code, but the fundamental hydrodynamics is much more similar between Castro, the Princeton code, and Flash. We use AMR. Similar resolution, although mine was slightly lower than theirs, but just slightly. And I tried to match everything else as best I could to what the Princeton group was doing.
Do you think the operator splitting makes a big difference here?
Well, all of these codes are operator split.
But I mean in terms of the direction. I guess
The directional splitting.
I think operator splitting would make a bigger deal than directional splitting.
Yes, yes, yes. I think so. I think so. The directional splitting, I think, would be important for perhaps the growth of instabilities and small-scale structure and anything that is sensitive to diffusivity. I don't think that the result of whether or not the thing explodes and on what time scale should depend on that. I really don't. So what did I find? So here's a couple movies. On the left is 3D, and this just is a slice of entropy through the meridional plane. And this is 2D, same parameters for these simulations, same resolution, same driving neutrino luminosity. And again, this is entropy. And so it starts right before bounce, and you saw the formation of the shock there. And it moves out, and immediately convection starts going in both 2D and 3D. But you see pretty early on a little bit of this up and down wobble along the symmetry axis in 2D. There's no preferred direction in 3D. It doesn't have that symmetry axis constraining it. And so it just kind of goes wherever it likes. And one thing that I hope you'll notice immediately from the movies, which I'll draw your attention to anyways, is that the structures, especially the buoyant plumes in 2D, are bigger, right, than in 3D. And this goes back to the question that Chris has already talked about, the inverse cascade. And I'll talk about more of that later. But in 2D, things tend to get bigger in terms of convection. And in 3D, they get smaller. Things get shredded apart. So what I found, and you can, if you're paying attention to the timestamps that you can't read, so, or can you even read the axes? Sorry about that. This is not very good. But what I found was that 3D explodes later than 2D, fairly consistently. And this was not actually the result that I expected to find. And so I checked, and I checked, and I recalculated, and I reran simulations. And it was consistently this, that 3D was harder to blow up than 2D. And so I got thinking, well, there must be some physical explanation for this. And I have some hand-wavy arguments for why we might expect this result. And they boil down to the fundamental differences between 2D with respect to, for instance, the inverse cascade. If you've got something that is convection-dominated like this, and it depends on the competition between buoyant driving force provided by the neutrinos and drag force, which is provided by the accretion flow from above, if you make a bigger plume, a bigger bubble, it's going to rise quicker. But in 3D, that big bubble shreds apart. Whereas in 2D, because of this inverse cascade, and because of the concentration of bubbles and convective plumes along the axis, which is artificial, they merge, and they get bigger, and they rise faster. There's also the problem with the axis exciting artificial growth of important instabilities, like convection, but also the standing accretion shock instability. So having gotten this result, I didn't update this reference. This is actually AppJ 775 or something like that, sorry. I thought it would be nice to repeat the calculation with better physics. And that's what Evan and I have been working on. So just
to go back, so you got the opposite result for the Princeton group.
Yeah, just completely diametrically opposite. So I'll just put this summary up there, actually. So just go there. No, it's okay. No. It's still unclear why the discrepancies persist between my results and the Princeton group. And our setups are much more similar by design than the Garchian groups. They're using a new code. The results did change a little bit from 2010 to 2013. But they're still finding that 3D explodes faster and easier than 2D. And that's just simply not what I found. And as I'll talk about, it's not what I'm continuing to find.
So for the non-experts, what's interesting, well, did the Princeton group use this light bulb?
Yes. They use the same exact light bulb. I got their source code routines and looked at it when we were trying to figure out what was going on. And I've implemented it exactly the way that they have in their code. So it's still very unclear. We're talking about how to solve this problem and how to do a code comparison. And that's actually something that I didn't put in the talk, but one of the things that came out of the micro meeting that Evan and I went to is an effort to do a rigorous code-to-code comparison for core collapse codes, but also just high-energy relativistic codes, and define a set of test problems that will break things down to sort of their component physics, gravity, hydro, EOS, and try to get at where the results are different, if there are differences.
Is there the gravity also the same?
No. So this is the thing that changed for them between 2010 and 2013. They found what Burroughs et al. 2012 calls a significant inaccuracy in their gravity solver, which they corrected in 2013. Yeah, he refuses to call it that. But
Is there any microphysics in these codes other than the neutrino transport?
Yes.
Velocity or
The equation of state is a very important component of the microphysics, and that is a difference between all of our codes, because each of these three projects used purportedly the same equation of state model. You know, Latimer and Zwesti with incompressibility of 180, right? We all say we're using the same EOS model, but these are completely different implementations, right? And so how you actually baked that soup of your equation of state and built the table that you're actually using in your simulations is completely different. And some groups are very proprietary with that kind of information. I'm using an open source equation of state, you know, and Evan doesn't write bugs in his code, so I don't need to worry about it. So it's unclear why these discrepancies are still hanging around. And I'd like to solve them. But in the meantime, I wasn't going to wait on that. I wanted to do something with better physics to try to get at this. Because if I was wrong, if 3D really is easier, and I was going out on a limb by saying it wasn't, if I was wrong, I wanted to be the one to prove it.
If it's hydro, you would think that the difference between dimensionality would persist in very simple, you know, ideal gas type equations.
Yeah.
Right?
Yeah.
There's some parameterized energy laws.
Yeah. Absolutely. Absolutely. I don't think anyone's done that. Rodrigo is in a very good position to do that, actually.
More or less the same as
Yes. In essence, there is a big difference in the Riemann solver. We're using a different Riemann solver. But I can't see how that would affect it enough to cause this. The kinds of differences that would introduce, I don't think would behave this way.
So you had in your table the optical depths were different, but did you
Yeah.
test that?
So if I change the optical depth and tune it like Honka do, it doesn't change 2D versus 3D. It just changes the normalization of the neutrino luminosity.
But do you actually tried I mean, I don't know what their exact optical depth as a function of density was. You do?
I do. I have their code. In fact, I had implemented their code.
Are you sure that's what they actually used?
That's what Jeremiah gave me. But he gave me the routine from Beta Hydro, not from Castro. So I don't know for sure, 100% for sure, what they actually used in Castro. So one of the things about this light bulb scheme, which we're already getting into, it's highly parameterized. And it left me with a bad taste in my mouth of, well, this could all be a result of this highly parameterized, overly approximate approach to important physics in this problem. So that's why we moved on to leakage. Leakage is not transport, but it approximates real transport a lot better than this light bulb approach. You get cooling of the protoneutron star, number emission absorption by the electron neutrinos and antineutrinos, and you get cooling by the heavy lepton neutrinos, which is important. And we also have a heating prescription due to the electron neutrino and antineutrinos, based on a derivation from Janke 2001. Important advantages over the light bulb scheme. The protoneutron star can actually cool and contract in a more realistic fashion, whereas in the light bulb, because of this high density cutoff, the neutron star doesn't cool and it doesn't contract. It just sits there like a big adiabatic ball, which is not what happens in realistic calculations. The luminosities are time dependent and calculated self-consistently via the leakage from the simulation, whereas in light bulb, the luminosity is fixed. And you get lepton number absorption and emission, which means you can capture the changes in the electron fraction in a more realistic fashion than this density-based prescription. And importantly, it's not dramatically more computationally expensive than just this local heating and cooling source term, especially in 3D, where the hydro is very expensive. So in multi-D, we follow... Not mine. With leakage, it's still hydro. Leakage about 10% of the overall hydro cost in 3D. Now that'll change when you go to lower dimensions because then it becomes a higher fraction. But in 3D, it's only 10 to 15% of the overall runtime. Hydro is still the number one user.
Is it gray?
It's gray. That's right. Yeah, this is gray. Yeah, that reference. It's Evan's scheme. So in multi-D, we follow audit all 2012 and 2013 and do a ray-by-ray approach. So the leakage is only computed radially along many of these rays. And then we interpolate the important quantities such as optical depth back onto the hydro grid before computing the local source terms. This is an approach that you can read about in these papers and eventually our papers, but it works fairly well. And the parameters of our simulation, so we ran a new set of simulations in 2D and 3D with different progenitors to look at this question again. We used higher resolution than I did before. This is pretty much the highest resolution of these types of parameter studies that have been done, I think. 3D Cartesian, less than half a kilometer resolution covering the neutron star and all the way out to 100 kilometers in radius. Beyond that, using the AMR, we decrease the refinement level so that you get an effective angular resolution of less than half a degree. So fairly high resolution compared to some of the other 3D stuff that's been done. And we use this many leakage rays for our ray-by-ray calculation. We use an improved gravity. So the earlier studies using light bulb all used a monopole gravity, which basically just means you integrate m as a function of r and use that to compute your gravity. Here we're using a new multipole approach, which I have a paper about, which should be printed in AppJ soon, which is much more accurate for this problem. It conserves momentum a lot better. We found some interesting tricks, which were fun math to work out. And we're using the good old Latimer's West equation of state, which you can download from stellarcollapse.org. So here's a summary of our results. And what we find is that 2D explodes for lower heating factor, or easier, than 3D for all of the models that we run. So in the leakage scheme, and I didn't put this equation up, there's a multiplicative factor out in front of the heating that we call the heat factor. Fiducially, this has a value of 1.0. And that's the value that we try to tune to match realistic transport. But you can turn this thing up, and you can get more heating so that you can drive explosions or more vigorous explosions. So what I'm saying here is that 2D explodes at lower heat factor. In fact, for a heat factor of 1.0, 2D explodes quite robustly, which is the black thin lines in the top plot, whereas 3D, for a heat factor of 1.0, fails to explode. And this is a 27 solar mass model, one that's also been looked at by a couple of other similar works in 3D, which is why we chose it. We also have a 15 solar mass model as well.
The 0.95 in blue, that seems to explode, is this 2D or 3D?
0.05, the 1.05? 0.95 is 2D, and that explodes. Yeah, so even when I turned the heat factor down by 5%, 2D still exploded. And an important point about this heat factor, it's not on this plot, but it's a later plot, is that this is a modifier to the microscopic heating efficiency, not the global heating efficiency. And because this is a coupled nonlinear problem, if you increase that microscopic heating efficiency a little bit, your global heating efficiency can go up by quite a lot because it pushes the shock out further and brings more mass into the gain region, which is in turn increases the heating. And I'll show a plot that demonstrates that later. So basically, the takeaway message is by increasing F heat by 5%, going from 1.0 to 1.05, we actually measured an increase in the global heating efficiency integrated over the simulation of about a factor of 2. So it doubled. So, some people, and some of my referees included, think that increasing this by 5% is a very small change. And so these models must be right there, right so close to explosion that they're marginal anyways. Well, actually, it takes a lot more oomph in terms of global heating efficiency to get these things to blow up. And this is just our knob that we can turn to achieve that. The other thing is, this is the standard deviation of the shock surface weighted by the mean shock radius. And what we see, these thin lines, it's a little hard to see on the projector, and I'm sorry for that, but 2D is universally far more asymmetric than 3D. So we don't evolve these long enough to see a kick. The center of the protoneutron star, especially with the new gravity, I don't think it moves by a grid zone.
So a little bit more about that tuning parameter. It's a free knob for you, but
It's a
what
free
is
knob.
it physically supposed to
Well,
capture?
it doesn't really correspond one-to-one to any physics. So you can't think of it like increasing the cross-sections, because that's not what we're doing. Because if we increase the cross-sections, that would change where the neutrino sphere was, which would change the spectrum, the mean energies of the neutrino. It would change everything. So this is literally just a free parameter on the microscopic heating efficiency, or microscopic heating source term. So I don't think it really corresponds physically to much at all.
Yeah. You can think of it however you like. You can think of it as increasing the luminosity, or increasing the energy, or increasing the number of target particles you're absorbing.
But without actually doing any of those things.
But it's a global parameter.
Well, this F heat is a microscopic parameter on the local source term.
No, but I mean, it's position independent.
Yes, absolutely. Absolutely.
Which is an assumption.
Oh, sure. Yeah. But the whole thing is a fudge factor.
I understand.
Yeah.
But the rest of the heating is all local.
That's right. So the
Oh, I understand, but
The amount by which you enhance it.
yeah is uniform. That's right. All right. So I kept you from this long enough. How about a movie? All right. So this is a 3D volume rendering of our 27 solar mass model, which does not explode. So F heat 1.0. The magenta surface is the neutron star. It's actually a constant density contour at 10 to the 12 grams per cc. The faint blue you'll see is the shock surface, and then you'll see the convection below that. So this is just right after bounce. Whoop.
that's 200-kilometer diameter.
That's right. So it recedes a little bit, and then the interface of the oxygen shell comes in, and out it goes again, tempting to explode, but it doesn't. And the shock recedes, and as the shock recedes, the gain region gets smaller, which drives the convective driving down, and eventually you get this very nice standing accretion shock instability, which has a clear spiral mode, so a m not equal to 0 mode. So that's what we find. Some global neutrino metrics. The luminosities we find are not too dissimilar from what you would get out of a realistic transport calculation. The energies, however, are systematically higher than what you get out of real transport. These are just mean energies. Remember, this is a gray transport scheme, or gray leakage scheme. And also the energy hierarchy is inverted. So really the new x's, which is the red line here, should have higher energies. Like I said, the protoneutron star...
You mean as a plotting mistake, or?
No, that's a feature of leakage. A feature of this gray leakage scheme.
Sorry, what is new X here? These are the other neutrinos?
These are the heavy lepton neutrinos. We group them together, that's right. So they all have pretty similar cross-sections and interactions in this context. So this is a common approximation, is just to lump all the heavy lepton neutrinos and antineutrinos into one species, which is what we do here. And this is the neutrinospheric radii. And so like I said, the PNS does contract and cool. This is a little bit faster than what you would find in a realistic transport calculation. And what we also find, the 1D are dashed lines here. Multi-D contracts a little less rapidly than 1D. This translates into some important quantities, namely the net heating rate in the gain region and the mass in the gain region. And then this is the global heating efficiency, which is what I was talking about before. This is defined as the net heating rate divided by the sum of the neutrino and electron neutrino and electron antineutrino luminosity. Sorry. So the black and green, this divided by the sum of the black and green, defines the efficiency of neutrino heating. So what I was saying before, so the black line, if you look at this, is typically below 0.05. The red line is more than 5% greater, despite only a 5% difference in the microscopic heating factor. Now, between 2D and 3D, we find systematically that for the same heat factor, 2D has more mass in the gain layer, which results in more heating, which results in easier explosions. This is caused, and I think I'll try to convince you of this, by the exacerbation, the artificial exacerbation of the important instabilities. The shock gets more aspherical. It elongates along the axis in an artificial way, which brings more mass into the gain layer. And this is a positive feedback mechanism. So you bring that more mass in artificially, you up the heating rate, which pushes the shock out even further. So it's a problem in 2D. And if we take a look between 2D and 3D, when we simulate something in 2D axisymmetry, this is what we're really looking at in 3D. All of those little bumps and knobs and convective plumes that look to be shredding apart are actually rings. And this matters for the hydrodynamics. They're rings. These rings are unstable in 3D. They won't persist. They'll break up. Right? And this is another reflection of this inverse cascade. Right? In 3D things, or in 2D things get bigger. In 3D they'll break apart and cascade to smaller scales. And this comes out if we were to compute the turbulent energy spectra. 2D is a little bit noisy. 3D is better. So what I've done here is to compute the kinetic energy density of the motion not associated with the background radial flow, which I relate to this sort of turbulent energy. And what we find is that in 3D, the exploding model has more energy, especially at larger scales, than the non-exploding model, which is important. 2D has a lot more energy than either of these two models at all scales. And importantly, the driving scale here should be around L of 10. That's about the driving scale of the convection, about half the width of the gain region. And you see, especially for the 2D model that's not exploding, it's flat to larger scales from that driving scale. And then it declines in a cascading fashion to the small scales. In 2D, it's essentially a solid power law all the way through the entire dynamic range. A little bit of noise here. We could probably fix that. So there's a big difference in the way that the turbulence behaves between 2D and 3D. Okay, summarizing. 2D explodes more easily and vigorously. This is confirming the result that I got before. It's also more or less consistent with the high-resolution simulations from the German group's parameterized calculations. I think the 2D symmetry axis is encouraging artificial growth of both the SASE and convection, and the inverse cascade is further exacerbating this problem by pumping energy to those large scales rather than cascading them to small. And buoyant plumes, which is a very important structure in these simulations, they remain large in 2D, and they are ring-like, which is quite artificial as compared to 3D. Now recently, the German group has published I didn't update the reference on this either, sorry, a full 3D neutrino transport simulation. Very, very expensive, but rather low resolution. But what they find excited me. This is the same 27 solar mass model that we do. And they find in 3D, the black line, it doesn't explode. The same 2D model with all the other same parameters does explode.
So what's happening at 0.2 seconds?
0.2 seconds is when the oxygen shell comes in. And you saw that in my models too. I think it was a little less pronounced, but that's exactly what's going on there right around 0.2 seconds, about the same time as well. That comes in and it sends the shock out a little bit. And it goes even further than 2D, but then recedes again, whereas 2D starts going. This is clearly SASE going on here in 2D, and then off it goes. So I think it's starting to converge on the solution that 2D is artificially easy to blow up as compared to 3D, which is important. It means we've got to do this in 3D. So the other question I mentioned, what's the dominant instability in these simulations? Is it SASE or is it neutrino-driven convection? Now, the Princeton group has been pushing the idea that in 3D, convection is dominant, and that the SASE is not important, especially for exploding models. It's not important. Some other groups have taken issue with this. And the German group looked at 2D general relativistic models with full neutrino transport, and they looked at 2 different progenitors, the S27, the one that we've been simulating, and a lower mass model. And they postulated that S27 should be highly susceptible to the standing accretion shock instability, whereas the low mass model shouldn't, and it should be convection dominated. And that's essentially what they found. They find 2 different regimes for these instabilities based on the progenitor structure. Some progenitors are going to show a lot of SASE. Others are going to be convection dominated. And Rodrigo Fernandez has a recent paper. I wanted to put a plot in there from his paper, but I couldn't decide on just one plot to put in the talk. But he goes into great detail with some very careful simulations in 2D and defines by linear analysis these different regimes for where we should expect SASE and where we should expect convection.
Now, when you say SASE versus convection, how close to an explosion is one getting here?
So the S27, I think both of these models explode.
Okay.
Both of these models explode. And this is another thing that Rodrigo goes into in his paper, is that it's not just an explosion versus non-explosion thing. Because that's actually what we see in our paper, is that the exploding models they don't have a very strong SASE. The non-exploding models, both of them show really strong SASE. But Rodrigo goes into this and shows that there is actually 2 different explosion regimes. Some explosions can be dominated by convection, while others are dominated by the action of the SASE. And I think that's also what's going on in these 2 2D models. It's important that they're 2D, I think. But here, the SASE is aiding explosion. Here, there is no SASE to aid explosion. It's possible. So, Auditol looked at the same 27 solar mass progenitor. This baby's getting some mileage. This is another not updated reference. Who was doing my references? And they looked at the standing accretion shock instability, and they found something interesting, which was the lower the heat factor. They use the same leakage scheme that we do, that Evan and I do. For a lower heating factor, you definitely got the appearance of a standing accretion shock instability. You turn the heat factor up, and it gets weaker, if hardly present at all. And the higher you turn that heat factor up, the weaker it got. And this is, you're driving more convection by turning the heat factor up. So it's just being outcompeted by the convection. And the explosion is setting in very rapidly as well. Now, in the full transport calculations of Hanke et al., they find a very clear evidence for the 3D standing accretion shock instability in their model. But it's an important point that it doesn't explode. So this is a model that has a relatively low amount of heating, which probably means convection's rather weak. And they sort of see this epoch of SASE right here. And then the shock recedes. It's small radii there. So we looked at this in our simulations of the 27 solar mass star, and we find clear evidence for actually 2 epochs of the standing accretion shock instability. On here, the 2D is the thin blue line. And you can see that 2D has larger amplitudes for the standing accretion shock instability than 3D. But 3D definitely shows a nice standing accretion shock instability. And this is a failed model in 3D. So after the shock recedes in this epoch, the SASE actually gets huge, which is what you were seeing in the movie, right? After that shock receded, the thing started to wobble around like it just didn't care. And we see this for both progenitors. So this is the 27 solar mass guy, and this is the 15 solar mass guy. And this is also the non-exploding model. And the interesting thing here is that at late times, we actually see a much stronger SASE for S15 than we do for S27. It's present at earlier times, but after that shock recedes, it gets really strong. I'll show you a movie of that. All right, so same everything as the previous movie, but this is now the 15 solar mass progenitor, which should be somewhat more favorable to convection. And during this epoch, we actually see that it is more favorable to convection than the 27 solar mass guy. But it still doesn't explode. There's still a weak SASE during this time. But after the shock recedes, which is going on now, it gets really big. So right about now, it's in the linear phase, and then it develops multi-mode, a spiral mode behavior for the 15 solar mass guy. So now what about turning the heat factor up? So what if we turn the heat factor up so that these 3D simulations explode? What happens to the standing increased shock instability?
Before you go into that, I mean, my recollection is that basically, if you think about the simplest constant gamma equations,
Mm-hmm.
the SASI appears as gamma is approaching 4/3 of the bottom. So the steeper the density profile, more likely you get the SASI. So that is consistent with the fact that as the shock recedes, the density profile gets steeper.
I think so. Shock recession is more favorable to the development of standing increased shock instability.
But there is a direct tie with the density profile there?
Yes, and I think that comes in, Evan can correct me if I'm wrong, that comes in more so in the mass accretion rate. So one of the reasons that S27 is so favorable to the SASI is that prior to the oxygen coming in, it has a very high mass accretion rate. And that accelerates the linear growth of the SASI.
Why? Why is high mass accretion rate accelerated linear growth?
Do you remember? I don't remember. I'll confess.
Because you can convect out any.
Oh, right. It must shrink the advective acoustic cycle. So it decreases the advective acoustic cycle timescale by having a higher mass accretion rate,
Let's talk about that.
I think. Okay, so turn the heat factor up and get an explosion in 3D. What happens to the SASI? We find something very similar to what Ott et al. Found. It gets weaker. And almost not present at all, especially for S15. I mean, I'm hard-pressed to point at anything as linear growth of the standing increased shock instability in this plot. It is present a little bit here for S27, but it is weaker. It has a longer growth time than it did for the lower heat factor. So here it seems that convection is winning the fight if you turn up that heat factor enough to get an explosion in 3D. So we find that SASI is evident in both progenitors during certain epochs, especially for the duds, the ones that don't explode. And it gets weaker if you turn that heat factor up as convection gets stronger. I didn't plot this, but the total power, if you were to sum up the L=1 modes, all the M's, is similar between 2D and 3D for the critical models, the ones that just explode. So if you compare models between 2D and 3D that have similar global metrics, such as shock expansion, heating efficiency, et cetera, the SASI is actually pretty similar between the two of them in terms of overall power in the L=1 mode. Okay, I think I have just enough time to talk about this last thing, which is, so we've been talking about 3D structure in the actual core collapse calculation. Earlier I talked about three-dimensional structure in real supernovae. Well, sort of the elephant in the room of all these calculations is that we start our initial calculations from spherically symmetric stars. Well, there is no such thing as a perfectly spherically symmetric star. So what if we perturb the star that we're using in our calculations in 3D? There are simulations, particularly from Dave Arnett and Casey Meakin, which show that in the late stages of stellar evolution, the convection in these stars, these massive stars, is very violent and very strong, particularly from oxygen burning and later silicon shell burning. And these can leave a huge imprint in both the velocity structure as well as the density and temperature structure of these progenitor stars that eventually create core collapse supernova models. And it's actually, if you think about it, using a perfectly 1D symmetric model, that we get from the stellar evolution people, which includes mixing link theory, and mapping it into 1D as a 1D structure into our codes is not self-consistent, because these things have mixing link theory to handle convection. They're telling you that these things are convecting over large regions of the stars, right? And it's important to the structure. So to do this in a completely 1D fashion is not self-consistent. So what Christian Ott and I looked at is perturbing the silicon-oxygen shell in a 15 solar mass star. We only perturb the tangential velocity, so the sort of theta direction velocity, with a large order perturbation. So, wavelength of typically, I guess, pi/2. And an amplitude, peak amplitudes that were picked from the simulations of Arnett and Meakin that looked at both silicon and oxygen shell burning. And these got up to peak Mach amplitudes of around 0.2. So that's what we put into our calculations. The actual integrated added kinetic energy, if you integrate over this entire shell, was small. There's only 10 to the minus 4 of the internal energy in that shell, and 10 to the minus 6 or something like that of the gravitational binding energy in the shell. So it didn't affect the sort of boundedness of the structure at all. We only perturbed the velocity. So what we get on the left-hand side is an unperturbed model, and the right-hand side is a perturbed model. And so what we find is that if you perturb a model that is close to explosion, you can drive an explosion for a model that would otherwise fail.
When you vect in your tangential velocity
Mm-hmm.
to the angle momentum, so tangential velocity going 1 over radius,
Mm-hmm.
what is your tangential kinetic energy behind the shock? Variable the thermal energy.
I think actually my next plot on the next slide, I think will answer that question. So I'll leave that to there. But what we see, of course, the red line is the exploding model. The black line is an unperturbed model for which we have not enhanced the heat factor. So this is an important point. We had to turn the heat factor up by 0.02. Now, if you remember before, I had to turn it up to 0.05 to get an explosion for an unperturbed model. So the difference between the black and the green line here is basically just the effect of the perturbations. Okay, these two models, black and green, have the same microscopic heat factor. And you can see that just perturbing it is the same effect on the global shock radius as turning up the heat factor by 2%. So this has a big effect. Adding these perturbations has a big effect, is my only point in saying that. And this, again, is the heating efficiency, the global heating efficiency of these guys. All right, so the next plot. So I think this plot will answer your question. So what I'm plotting here is the anisotropic Mach number. So the Mach number of the anisotropic flow in two different regions. One, the gain layer, solid lines. Two, in front of the shock. And this is multiplied by 10. Okay, so this is right in front of the shock, and then this is the gain layer.
So the only lower curve is multiplied by 10.
That's right, that's right. This curve is multiplied by 10 because there's a huge disparity, of course, in the difference in the Mach numbers. So what we see is that the perturbed models, whether they explode or not, have higher anisotropic Mach numbers in the gain region than unperturbed models. And importantly, so this blue line is the anisotropic Mach number from an unperturbed model. So this is setting our baseline, right? This is the anisotropic motion due to grid effects. Okay, because I'm using a Cartesian grid, and this is basically a spherical problem. So these are the grid effects. And this is how much more we're perturbing this model. Okay? And you see this time-dependent behavior because of the radial dependence of the perturbations that we added. So you're basically getting two nodes from the silicon-oxygen core. And another way of looking at this, no, I just pointed at that myself, is to make plots in spherical harmonic space. So this, again, is the anisotropic kinetic energy density as a function of L. And this is the spectra of the perturbations in both density and tangential velocity. They're basically the same. The lines are essentially on top of each other everywhere except right here. Okay? So we're injecting these perturbations at about this scale. And then because of compression and lateral motion during infall, they kind of spread out. But basically, this is the scale at which we're putting these perturbations. And this is pre-shock. And if we looked at the gain region kinetic energy density for the two critical models, the one that doesn't explode is blue and the one that does explode is red, we see that there is significantly more energy in the exploding model on large scales, starting at about where we put the perturbations in. And at small scales, they begin to converge in terms of their kinetic energy densities. So the story here is that by adding these perturbations, we're encouraging stronger turbulence and convection in the gain region. And that stronger convection and turbulence in the gain region is resulting in longer dwell times in the gain region, and therefore more neutrino energy absorption. And that can push it over the critical threshold, and you can get an explosion.
Question about your anisotropic Mach number upstream.
Yeah.
That is reference to the sound speed downstream?
No.
No, it's reference to the sound speed upstream.
That's right.
It's low.
It's low.
So which means that if you think in terms of the tangential velocity itself, it's even lower relative to the solid curves because the sound speed.
That's because the sound speed is different, yes. These are really mild perturbations. I mean, really, they're not super strong perturbations. We were trying to be exceedingly conservative. So,
And also,
Yeah, yeah.
how long does it take for one, you showed that in the progenitor, you have this reversing velocity, right? So it cells.
Mm-hmm.
How long does it take one of those structures to vec through compared with the time for stuff to settle below the shock?
I can't say that for sure because I would have to do something, I think, like a Lagrangian tracer calculation to actually follow one of those perturbations through the gain layer.
But that is relevant. Right?
It is relevant. It is
You're
relevant.
exposing it to a consistent sense of
Right.
flow, transverse.
Right.
Which would be sort of like adding some rotation, it sounds like, if that were the case.
Yeah. I don't think I said this explicitly, but I hope from the picture it was clear. The net momentum of this is 0, right? The net momentum is 0. Okay. So there are large qualitative differences between 2D and 3D. And so we got to study core collapse supernovae in 3D. It's just got to be done. And progenitor asphericity qualitatively alters the post-bounce evolution. So we got to study progenitor evolution in 3D too. And this is still a big open question and problem in core collapse theory, which I hope some progress will be made on soon. Anyways, I think I'm exactly at 1 hour. So thank you very much for your attention. And I'm happy to have questions.
Any questions?
Yeah.
Maybe a naive shot in the dark here, but is there any way to actually make the real life be more 2D by adding rotation or magnetic fields or something like that? Since these seem to explode.
Yeah, rotation could make things behave more 2D, but I think in order to make things 2D in the sense that the effect would be similar to imposing a symmetry axis, the rotation would have to be really high and really dynamically important.
Progenitor would be rotating like that.
Well, in the collapsar case.
In the collapsar case,
Okay, sure.
yeah.
Only extreme case.
But just for a normal isolated.
For a normal isolated star, it'd have to be rotating. Yeah, there's no reason to think that they rotate that rapidly enough to be quasi 2D in 3D. Yeah, but that's not naive. That's a good point. I answered everything so thoroughly in my talk. No more questions?
Wow, actually, that's lots of parts, but you're very interesting, most recent paper. It's fascinating.
It's a tantalizing result.
I guess I'll ask then, what are the plans to develop more realistic progenitors? Because throwing down some perturbations might be nice. But what you'd like, obviously, is for someone to hand you a realistically generated progenitor.
So I know that Dave Arnett and Casey Meakin have been working on this. And they've done some of the only 3D calculations of any part of stellar evolution. And they are driving toward more realistic 3D simulations closer to the collapse phase. I don't know how close they are to doing something where they could hand a supernova simulator a structure. I know Dave is working very hard on improving mixing link theory so that the 1D structures of these things are more realistic. That's good. The other thing, which is something that I've thought about, is a better way of laying down a perturbation on these stars. And what we're working on is a vector spherical harmonic framework, which, given some power law index of your perturbations or of your turbulent velocities, you could put things down on the star that looks like convection. You know, you would have vortical motion in these sort of large scale. Right, exactly. Those don't look like much like convection. But if you do this in a spherical harmonic basis with radial Bessel functions and Dirichlet boundary conditions, and you enforce, net Kelvin-Helmholtz growth of 0 at the boundaries, you can get something for the velocity field that looks much more like convection. And then you can set the scale. You know, you can say, okay, it's L equals 2, or it's L equals 3, or it's L equals 4, and then you can get more realistic perturbations. And that's what we're working on for future work. And I think hopefully combined with more realistic 1D structures, that's going to be progress. But the Holy Grail is still a realistic 3D progenitor simulation that goes all the way to collapse. And according to Dave, you don't have to do much. You don't have to do the entire star's life, which of course is impossible, because the convective timescales are so fast. The Brunt-Weissler frequencies are very small that you might be able to get away with a minute.
Just as long as it doesn't feed back something on the structure.
Right. Which it might, because you're initializing from a 1D structure.
Well, a 1D structure that, in some sense, is taking these things into account.
Right.
I mean, when Dave takes his 1D models and puts them in 2D, maybe his convection zone grows, but
Yeah, well,
it's not completely different. Except
he's not showing you the first 100 seconds or so of the evolution. That's great questions.
maybe we can save questions, the rest of the questions for cookies.
Yeah. I'm here tomorrow too, so
And you'll be giving a talk. Is there a gravity meeting tomorrow?
There should be a gravity meeting tomorrow.
What's on the schedule?
He's on the schedule.
I'm on the schedule. What do you want me to talk about? All right.
What do you want to talk about? Yeah, so a gravity meeting tomorrow. Hopefully
All right.
John will join us, so we have more time to talk.
Cool. Thanks, everybody.